Welcome to another Kodiak project video. My truck is in sport mode almost all the time I'm driving it, and it has become bothersome to have to rotate the mode knob each time I take it out. In this project, I'm going to fix that. Now, right from the beginning, I can't do what I really want. That is, to make it remember what mode it's in and always restore that mode the next time the truck is driven. This is because there's no easy and reliable way to know what mode the truck is in at any time. So my actual plan is to do the next best thing. I will add a 3-position knob with settings for normal mode, sport mode, and off-road mode. This knob will be set and forget. Turn it to sport, and it stays there. Then, a circuit I will design will electronically rotate the mode knob as needed to restore whatever mode I selected at startup. If I select sport, it will always start in sport mode until I say otherwise. That I can live with. I was able to do this by modifying a replacement switch so everything can go back 100% stock just by swapping the original switch back in. The switch was pretty easy to disassemble, 2 screws and a few tabs. So to start with, let's get this apart and get the multimeter and see what happens when you rotate that mode dial. I was glad to see no integrated circuits on this board. It's pretty simple. Contact pads for the buttons, the switch for the mode dial, LEDs for backlighting, and a bunch of resistors. So this little guy does the magic. The knob pushes this toggle left or right when you rotate it left for tow or right for mode. Now, only one of these contacts, the common pin in the center, is actually directly connected to a pin on the headers where the truck wiring plugs in. I suspected as much from looking at the connector diagram. I'm not sure why it was done this way, but to do this safely, I will activate the switch by shorting the pins on the switch itself, and let the factory circuit do the rest. This is why the modification was done inside the switch rather than on the truck side harness. However, for how easy it makes to reverse the mod, I actually like it this way. Let's test the switch and make sure that I know which contact is which. This is the common pin on the toggle switch. It's the only pin directly connected to the header, which plugs into the truck harness. When the knob is rotated clockwise, or to the right for mode, the toggle is pushed to the left. When the toggle goes left, the center pin and the pin on the right are shorted together. Those are the contacts I need. This is the schematic of the circuit I designed to do this job. 4 connections to the factory mode switchboard. I can get ground and switch 12 volts from there, making for a clean install. The second connector goes to the 3-position rotary switch to determine what the default mode will be. This is the power supply circuit. I need 5 volts for the controller. The microcontroller is an 8-pin Atmel, 8-bit 1 MHz MCU. Based on the mode selection dial, it will close the mode switch contacts 0, 1, or 2 times to select the mode I want. This part of the circuit is the small solid-state relay, which will short the pins of the mode selector switch, controlled by the MCU. Pretty simple, huh? This is the actual printed circuit board layout. It has all the components shown on the previous schematic. Power supply, microcontroller, mode switch relay, here's a better view of what the board will look like when it's finished. It's possible to get professionally constructed PCBs ordered by a number of made-to-order board houses around the world. They can send you production-grade boards ready to get you soldering on components, but I really like the satisfaction of building them completely myself, at least for the prototype phase. First, I print out the PCB artwork. This is a light box I made. For the board to turn out correctly, the top and bottom of the PCB design must be in perfect alignment. They are taped together to form a pocket that the PCB board fits into. PCB making involves some hazardous chemicals. Be sure to have safety gear like rubber gloves and chemical-safe goggles. When picking rubber gloves, also, make sure to get the ones with strawberries on them. They're the best kind. Preparing the ferric chloride etchant solution. This must be heated to around 50 degrees C for optimal etching. So I will get the tank started first and get it started heating. I use an electric heater to warm it and an air pump to agitate the solution. Yep, that etchant tank is actually a breakfast cereal container. It's the perfect shape after all. This is the PCB blank itself. It's a positive, pre-sensitized board. So you can use that design I printed, expose the board to light, and the PCB design will block the light where the traces need to be. And then the resist can be developed, which allows the etching process to work the way we want. I was actually surprised to find this board has no protective film over the exposed resist in the bag. I've never seen that before. So I protected it from light with painter's tape so I could cut the board down to size. The board with its resist exposed is then placed inside the sleeve of tracing paper with the PCB design printed on it. It goes inside the pocket I made, so the board sits between the two sheets of tracing paper. Then the glass is applied top and bottom and clamped. This keeps the PCB design held tight up against the board and prevents it from moving during the exposure process. Then the board is placed under the light. This isn't even a UV light, it's just a standard fluorescent tube, which of course does produce an amount of UV. This is the bulb that the PCB manufacturer, MG Chemicals, recommends. The light is turned on and the board is exposed for about 15 minutes for each side. While that's going, let's get the developer solution ready. 1 part developer to 10 parts water, in this case 50 milliliters to 500 milliliters. This solution develops the resist. Any resist that was exposed to light, wherever the PCB design allows the light to shine through, is developed away, leaving only resist where the PCB design had black toner. This process takes about 10 minutes or so, but it can vary, especially based on the temperature of the developer. How cool is that? Once the board is developed and rinsed, it's into the etchant bath. The ferric chloride dissolves almost any type of metal, including copper from the board's surface. Wherever that green resist is, the etchant can't penetrate, so any exposed copper is removed, the resist-protected copper remains. I check the board about every 5 minutes. It's important to stop the etching as soon as the board is there. Never mind that second one, that's for a different project. This looks good now. The board itself is rinsed with plain water, and this is the result. Here you can see some damage to one of the PCBs. This process is rather error-prone. I'm building 2 boards here, a primary and a backup, so when I went through the process I made 4 copies of it. This isn't always necessary, but this way I can pick the ones that come out the best. Back to the Dremel saw. I'm cutting the individual board out. This saw is great for this purpose. FR4 is a fiberglass reinforced medium. It's very hard on saw blades. It destroys them quite fast. This saw uses cheap and easy to find T-shank jigsaw blades. It's basically a jigsaw upside down with a table on top. The blades last long enough to get through several boards before they need to be replaced. I use metal cutting blades for this. The green resist can be left on the board permanently. It's actually designed to be soldered through. It will vaporize under the heat of soldering, but I like to remove it and tin plate the boards. For one thing, they look so nice with the resist off. Resist is removed with acetone. Unfortunately, the board can't stay like this. The copper will oxidize. It must be protected with a flux pen, or as I prefer, tin plating. This stuff has the scariest of all warnings of any chemicals I use in this process. The board goes in a bath of this stuff, and it chemically plates the copper with tin, giving it a silver look. For some reason it always ends up looking blotchy. Maybe I need to clean the board even more thoroughly before this process. But it does the job, and this will be hidden once the project is done anyway. Now off to the Dremel drill press and a set of drill bits a fraction of a millimeter in diameter. Using this setup, all of the through holes in the board are drilled out. The center hole allows the thickness of the copper to guide the bit into the center of the hole, making this process easier. Even with the guide, I sometimes still miss center. This view is shown through a microscope. With the holes drilled, the next step is to connect all the vias. This is where the circuit trace from one side of the board passes through the board and must connect to the other side. This must be done for routing purposes, to allow traces to cross one another, or to avoid where components are located. There are a number of ways to do this. What I do is take a single strand of copper from a piece of stranded wire and feed it through the vias, solder on top and bottom, then cut the wire in between. It's about the simplest way to pull this off. This is one of the resistors on my finger. I use a lot of SMD components to save space on the board. SMD components are also a lot cheaper than their through-hole counterparts and much easier to find. It's actually surprisingly easy to solder these tiny components. This one is about 0.8 millimeters long, and that's the longest dimension. I need to use a set of loupes, or head-mounted magnifying glasses, to see what I'm doing when soldering these kinds of components. They must be handled with needle-tipped tweezers. You'd never be able to hold them by hand. To solder these and other small components, I pre-tin the solder pads, then use the hot air station, which is basically a heat gun with a really small nozzle. I reheat the solder to melt both pads at once, and then use tweezers to place the component where it belongs. Once the solder bonds to it, I take the heat away, and the solder quickly solidifies, securing it in place. I use a very fine tip on my soldering station and the thinnest solder I can find for this. These pads are about 2 millimeters across, and those are the big ones. The SMD pads are smaller. In case you wonder, the markings on these indicate the resistance. You take the first two numbers, and then for the third number you add that many zeros. So in this case, 1, 0, and then 3 more zeros, or 10,000. These are 10 kiloohm resistors. Notice how pitted the PCB traces are. This is just the nature of the photoresist method. I'm not sure if I don't have the technique down quite right, or if this is just the way it is for everyone, but I compensate by making the traces generously wide. It's easier to make any repairs if the board comes out badly that way, and it makes the board more resilient to such imperfections. Ah, this is crooked. Must fix that. I start with the smallest components and work my way up to the bigger ones. The smaller ones are easier to install when the board is otherwise empty. These are capacitors and an MOV, or metal oxide varistor, part of the power circuit. Sometimes it's difficult to avoid reflowing the solder on nearby components by accident when installing new ones. It's best to be quick. This 3-pin device is a transistor, an N-channel MOSFET to be precise. It acts as a switch to activate the solid-state relay. This is an LED which turns on when the board has power. You won't be able to see that once it's installed, but it's for diagnostics. The second LED turns on whenever the circuit is actually closing the mode switch. This is the SSR itself. I usually use the smaller version of this part. It's identical, just in a smaller package. Unfortunately, it was sold out everywhere. The 2022 semiconductor shortage affects us all. This is a socket for the MCU. I would ordinarily use an SMD component for the processor, but in this one case it actually saved me space on the board to use the larger through-hole version. With a socket, I can program the chip and then install it on the board. I don't need to add provisions to connect a programmer to get the firmware onto it this way. Moving on to the next task. I put the switch back together for measurements. Since I already showed its disassembly, I will go through this quickly. My first plan was to mount the circuit board in a case right to the back of the switch itself. Unfortunately, there isn't enough room, so I will have to put it elsewhere. Okay, let's solder some wires onto the mode switch board. The first pair to go, the contacts for the toggle switch that cycles the mode. In this case, I am soldering a wire onto the SMD leads for the switch. There's only a small area where the wires can fit around the circuit board inside the case. There's not much room between the switch casing and the edge of the board. That's why I'm routing the wire like I am. This is where I was able to make them fit. The third pin on this switch is the toggle for tow mode. I'm not connecting that one at all. I had to slit the rubber piece in order to make room for the wires. This must be done carefully. This part is not only the spring for the 4 transfer case buttons, but also has the contacts that make the buttons work, so the cut needs to be made where it won't have any effect. Just to double check, using the meter to make sure the wires are in contact when the knob is rotated to toggle mode. All good. This shows the very small area where I was able to route the wires. It's so tight I had to have only one wire per side, but it all fits. I really wanted not to cut or modify the switch body, so I'm glad that there was enough room. There are 2 more contacts needed, the switched power and ground. I will get those right here. This makes for a clean setup. All the connections to the truck wiring are done right on the switch itself. Sorry for missing the action, for some reason I kept getting in the way of the camera. Pin 5 is ground and 6 is switched power. When looking at the connections from this angle, those are the 2 lower left side pins. After a quick check with the meter to ensure good connections and no unexpected shorts anywhere, the switch can be reassembled except for the back plate. There I must make a cut to pass the connector through. There is space between the circuit board and the back of the switch, but not much of it. Wire routing must be done carefully. I also had to modify that part of the switch to make a little room. Now this part of the project I had to redesign later. I thought the connector alone would still fit here. It almost did. I needed just a couple millimeters of extra space. For now, I'm just going to pass the wires through the back of the switch, so the connector can just be free. The hole I'm about to cut is needed either way. I will consider leaving it like this or using a lower profile connector. I cut the passage with a hot knife. I had to remove some of this plastic to make room for wires. All this does is hold the PCB firmly in place. I left enough of it to still do its job. This was the original plan, the connector attached right to the switch. Just a few extra millimeters and it would have worked. Okay, finishing the board's external wiring as well as programming and installing the microcontroller. These wires plug into the connector on the mode switch that I just installed. Onto the MCU. This is a tiny ISP programmer made by SparkFun and designed specifically for this particular MCU. The chip plugs into the socket on the board and the whole device plugs into the computer with USB. The software is written in C++ using the Arduino toolchain plus a number of libraries I wrote myself years ago. The development environment is Visual Studio Code using Platform I/O. This setup worked quite well. The download process burns fuse bits on the MCU to configure it and downloads the software onto the chip. This only takes a few seconds. Once programmed, the chip comes off the programmer and plugs right into the socket on the board. Next, I need an enclosure for the device. It must be protected. I built the enclosure to be as small as I could, and built it with a 3D printer using ABS plastic. The bottom piece gets these M2 heat-threaded inserts so the enclosure can be assembled with M2 machine screws. Here I'm using my Dremel drill press again with a customized bracket I modified from one I found on Thingiverse. It clamps my welder soldering station's iron to the drill press. Using a threaded insert installation tip, this allows me to use the drill press to push the inserts in accurately and with the aid of a depth stop. Okay, now to install the prototype and see if it works. Ignore the wires here that make it obvious that this is actually a dramatic recreation of the first test install. 2 15s and this panel pops out. There's also a little tab on this one side that needs to be pushed outwards to release it though. There are 2 connectors, one for the headlight switch, one for the mode switch, after which this whole piece comes free. The mode switch itself just snaps into this bracket. Release 4 clips and it comes right out. All that must be done is replacing the original switch with my modified one. What you're seeing here is temporary since I had to modify where this connector goes. Once the project is completely done, it will look more professional, although you'll never actually see this part. The auto set sport board plugs in, and now I'm just hiding it behind the panel. I will eventually tie it to the wiring harness so it can't move around. Now this part I haven't actually talked about at all during this video. That's because it's just a temporary piece for testing the prototype. I have a few different ideas of where this knob will be located, but I haven't decided which one I'll pick yet. Once this part is done, I will have all of those details. This knob is a 3-position rotary switch retained position, so all you have to do is set it to sport, for example, and it stays there forever until you have reason to choose a different startup mode. And no, those are not the final colors for this either. I just printed it with whatever filament I had laying around. Okay, the big moment. Let's start it up and see if the mode changes on its own. I will not touch the mode dial at all. Lyra Silvertail is impressed.
What do you think about that, Lyra?
Let's try again. This time, default to off-road mode. This requires 2 virtual turns of the mode dial. There we go, it works. The last mode is normal mode, or what I prefer to call touring mode. When the knob is left in this position, the circuit does nothing and allows the startup to happen normally. Lyra Silvertail is bored now. She wants to go for a car ride. And actually that's where I'm going to end this one. There's still work to be done. finalize the switch modification, mount the enclosure, and most importantly decide on where to install the default mode knob and design the final panel and knob for it. But right now, for this project, I want to leave it like this for a few weeks just to make sure everything continues to work exactly as expected. I will be back again for a part 2 before too long to show all the final steps of this project. Having had this installed for a week or so at the time of making this video, I'm loving this fix to remove one more annoying feature that GM built into this otherwise amazing truck. I still have to fully retrain my brain not to reach for the mode switch immediately after pushing the engine start button every time, but I'm getting there. In case anyone is wondering, why is this so important to me? Why go through all of this just to keep the truck in sport mode? Is it really worth it? Well, for me, it was. I like the way the truck drives in sport mode much better. It's my everyday setting. Sport mode arms a kind of spirited driving behavior detection. When you drive the truck hard, it automatically shifts gears faster, maintains lower gears much more readily, downshifts quicker, and will hold off on upshifting a bit longer. It observes how you are driving and enables these settings, which GM calls performance shift features, and returns to a more casual shifting pattern when you're not driving it aggressively. Furthermore, for trucks equipped with magnetic ride control, such as this Denali is, it also stiffens the suspension to provide better handling. I do use all of my truck's modes, however, but I only use normal mode, which provides a softer, more comfortable suspension feel when on long trips on the highway when comfort is more important than performance. I also use off-road mode sometimes. It's great for unpaved or poorly maintained roads. It's also a great mode to use when driving through deep snow. But in any other situation, sport mode it is. And now, my truck actually agrees with me. Thanks for watching!